So Adam is our second keynote speaker who just landed in Stockholm and ran into the conference. He's from far, far, far away, from Malmö. He missed Stockholm so much. The last time he was here was so long time ago, on Friday. So welcome everybody.
Thank you very much, and good afternoon, everyone. It's a true pleasure to be here. And what we're going to do today is that I'm going to take you with me on a quest for a crystal ball. A crystal ball that will help us to not only identify, but also to prioritize technical debt. So let's jump right in and see what this is all about. So my starting point is Martin Fowler's well-known definition of technical debt. And I think most of you are familiar with this, so I want us to focus on the key aspect here. And the key aspect of technical debt is that, just like its financial counterpart, technical debt means that it incurs an interest payment, right? Our code becomes a little bit more expensive to maintain than it necessarily has to be. And I found that this is something that we, in the software industry, tend to misunderstand and sometimes even misuse. And the consequence of that is that technical debt, the very concept, is not as useful as it could be. So let me show you what I mean about that. And the way I want to show you is by having you do a small experiment here. You really weren't prepared for that, right? So what's going to happen now is this. I'm going to show you a piece of code. It's not going to be Python, but it's going to be a piece of code. And your task is to judge the quality of that piece of code. Are you ready? Yeah, that's great. That's the spirit. Perfect. So here we go. Have a look at this wonderful beauty. How many of you think that this is fantastic code? 1, 2, 3. Oh, great. How many would let this through a code review? So just 3 of us. Cool. I'm in good company there. So I would claim that this is not necessarily the best way to solve this particular problem. I would also claim that this is not really particular good code. And it's of course code that we will never, ever write ourselves. But is it a problem? More importantly, is it technical debt? It turns out that without more context, we really cannot answer those questions. Because technical debt means we have to pay an interest rate on it. An interest rate, that's a function over time. So in order to decide if this is technical debt or not, we would actually need a time dimension into our code. So where can we get such a thing? Well, in a few minutes, I'm going to show you one possible way. But before we go there, I would like to share a story with you. So as part of my day job, what I normally do is that I go to different organizations, I analyze their code bases, and I try to come up with a list of the prioritized technical debt and suggest some recommendations. And a couple of years ago, I worked with an organization in the UK. And prior to my arrival, they had done something pretty interesting. They had run a tool that's capable of quantifying technical debt on their code base. So they had taken this tool and thrown it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. So 4,000 years of technical debt. Just to put that into perspective for you, 4,000 years ago, that was here, when Moses parted the Red Sea. So I think my point here is that 4,000 years of technical debt, it might well be accurate, but it's not particularly helpful. I mean, where do we start? Is all debt equally important? And besides, I also think it's a mistake to quantify technical debt from code alone. And the reason I say that is because most technical debt isn't even technical. And again, this is something I find over and over again when I work with different organizations, that we developers, we tend to mistake organizational problems for technical issues. And the consequence is that we start to treat symptoms instead of the real root cause. So just to give you some examples on what those symptoms could be, you might come into a new organization and someone tells you that, hey, be careful with the code over here. It's really, really hard to understand. Or we have a lot of defects over in this part. I really wonder why. And then, of course, we have my personal favorite. You might have heard about this one, that we spend a lot of time merging our different feature branches. We need to buy better merge tools. Yeah. So as you might see, there could be on social or organizational aspect an explanation for those. And I think the reason that we make this misattribution is because there is a very strong link between technical debt and organization. But the problem is that the organization that builds the code is invisible in the code itself. So that's why it's so easy to overlook. And I'm pretty sure that we will never be able to take a holistic view of technical debt unless we also include a social and organizational aspect in it. So based on what I've told you so far, I've raised a number of potential issues. And what I'd like to do now is to approach some solutions. So I put together kind of like a wish list on the kind of information I would like to have in order to prioritize technical debt. So I'm going to show that list to you, and I really hope you agree with me that that information is useful. Otherwise, it will be a short keynote. So my starting point is that the first thing we would like to know is, where is the code with the highest interest rate? Which code is truly the most expensive to maintain? And second, what about our architecture? Does a software architecture support the way our system evolves? Are we working with or against our software architecture, which is actually quite common? And third, and perhaps even most important, is how does this look from a team perspective, from a social perspective? Do we have any parts of the code that become coordination bottleneck? You know, those parts where 5 different teams have to work at the same time all the time? So have a look at the list, and I hope you find this useful. Now, the interesting thing with this list is that none of that information is available in the code itself. You pick up a piece of code and you cannot answer any of those questions. So most importantly, we lack a time dimension and we lack social information. So where can we get that data? Where's our crystal ball? It turns out you all already have one. We're just not used to think about it that way. I'm talking about this, our version control data. I'm a big fan of version control data. And yeah, I guess we all have our odd hobbies, right? But the reason I like version control data is because, first of all, it gives me a time dimension. So we know exactly when each piece of code was modified, and we can use that to calculate a lot of interesting statistics that we're going to have a look at soon. Second, version control data is actually social data, because our version control data knows exactly which developer that changed which piece of code and when they did it. So let's embrace version control data, and let's see how it might help us to find code with the highest interest rate. And what I want to show you now is an analysis I call Hotspots. So let's have a look at a piece of code here. This is a hotspot analysis of a well-known code base. Some of you might have used this code base, actually. This is Tomcat. Has anyone worked with Tomcat? Oh, yeah. A lot of victims. Perfect. Has anyone looked at the Tomcat code? Yeah, some of you. Great. So this should be familiar to you. What I want to do now is to just, the reason I use Tomcat is because it's an old, mature code base. It's written in Java, and it has a rich history. So it's a pretty good starting point. Now, what I want to do is to walk you through this visualization so that you know what you see. First of all, you notice those large blue circles, the one that blink on screen right now. Each one of those represents a folder. So this is a hierarchical visualization that kind of follows the folder structure of your code. So if you're familiar with Tomcat, you will recognize each one of those as different packages. It's also an interactive visualization, so I can zoom in to the level of detail I'm interested in. And when I do that, you will see that each file is represented as a circle. And you see that the circles have different size. That's because the size of the circle represents the complexity of the code. How hard is that code for a human to understand? And you might want to ask, how do you calculate code complexity? And as you might know there are several ways to do that. We can use things like cyclomatic complexity, we can use cognitive complexity, we have Halstead's volume metrics. And basically, my advice is that you can use any metric you want, because what they all have in common is that they're equally bad. We simply don't have a good way of measuring complexity in a meaningful way. So what I recommend is to use the simplest possible proxy that works, and that's the number of lines of code. There's actually a very strong correlation between number of lines of code and those other metrics. And besides, this is not even the important dimension, because the important dimension is this. How often do we actually have to work with the code? The more often, the higher the interest rate on any potential technical debt that we might have in that code. So we visualize that using color. The more red something is, the higher the change frequency of that code. The more often we work on it, the more commits we do. And the interesting thing is when we combine these two dimensions, because now we're able to identify complex code that we have to work with often. And that's our hotspots. So let's return to Tomcat. And as you see in the visualization, there are a few hotspots in Tomcat. And a hotspot doesn't necessarily mean that we have a problem. A hotspot just means that this code is a little bit extra important, because this is the part of a code where we do most of our work. So these are parts of the code that we need to keep simple, easy to understand, and easy to evolve, and easy to extend. However, in practice, more often than not, I've found that the opposite is true. And that tends to make hotspots excellent refactoring candidates. And there's a very fascinating reason that works so well. So how many of you have ever read something from George Orwell? Please keep your hand up if you read The Animal Farm. Ah, cool, great. So it's a fantastic book. And those of you who have read it, you might recognize the following quote, because George Orwell wrote in that book, he claimed that all code is equal, but some code is more equal than others. And the first time I read that book, I couldn't really get what he was hinting at. But then I realized what George Orwell was referring to was this. He was obviously referring to the following graphs. So please have a look at them. Each one of those graphs shows exactly the same thing. You have on the x-axis, you have each file in a system. And they are sorted according to change frequency. That is, how many commits do we do to that file? And the number of commits is what you see on the y-axis. Now, if you look at my examples here, I have 3 different code bases, 3 radically different code bases, implementing different programming languages, targeting different domains, developed by different organizations, different developers, different lifetime spans. Everything is different. And yet, do you see any patterns? That's right. They all show exactly the same thing. They show a power law distribution. And this is something I've seen in every single code base I've analyzed so far. And I think I analyzed like 200, 250 different code bases. So this seems to be the way that software evolves. And this gives us a tool to prioritize technical debt. Because what this basically means to us is that most of our code is here in the long tail, which means it's rarely, if ever, worked on. So what we want to do is to use the hotspots to identify the head of the curve here and look for any opportunities to improve that code, because this is where we have our highest interest rate. So hotspots are a very good starting point to prioritize technical debt. But sometimes hotspots are not enough. And I want to show you an example on when hotspots don't work well enough. So how many of you have a laptop with Windows? Some of you. Cool. So then you might recognize the following code base, because it's something you're likely to have executing on that laptop. This is a hotspot analysis of .NET Core, the runtime from Microsoft. And when I did this analysis, I think it was a year ago, most of the hotspots were here in something called JIT. So that's part of the just-in-time compiler. Now, at that time, they did a major restructuring of that part, so it's quite natural that a hotspot show up there. But what fascinated me was that there was some kind of satellite hotspot here. A hotspot called gc.cpp. That's the .NET garbage collector. And gc.cpp, it might look quite innocent here in this visualization, but that's only due to the scale of .NET Core. .NET Core is big. So what you see here on screen is 4 million lines of code. And gc.cpp is a big, big file. How big? I have no idea. So let's look it up at GitHub together. Here we go. It's that big. So what we need to do here is we need to look at the raw file, and what we find is 37,000 lines of C++. 37,000 lines of C++. Do we have any C++ developers?
Not anymore.
Yeah, former, cool. You're in good company. I used to do C++ for 10 years, and I know what you think. It's 10 years I never get back. And it's, yeah. And yeah, it's true, it's true. But what I want to say with that, I don't just want to bash C++. What I want to say is that I can really sympathize with that, to have to maintain 37,000 lines of C++. It's a true monster, right? And besides, how useful would it be if this was your code, and I got to your organization, and I told you that, hey, look what, I found your worst maintenance problems. You just rewrite that file and everything will be fine. Again, it would be correct, and it would be true, but how useful it is. How would you act upon that information? The answer is, you won't. You need much more detailed information. So what I do when I come across those gigantic files is that I use a technique I call X-ray. So what I do here basically is that I take that big file and then I parse it into the different functions. Then I look at where do each commit hit inside that bigger file. So I basically get hotspots on a function level. Let me show you an example from gc.cpp. We can see that inside gc.cpp, our number one hotspot on a function level is something called grow brick card tables. And we see that it's a pretty big function, 332 lines of code. So that's kind of a lot for a single function, isn't it? But it's much less than 37,000 lines of code, which was the size of a total file. And it's definitely less than 4 million lines of code, which was the size of a total code base. So even more important, we are now on a level where we can actually act upon this information and do a focused refactoring based on how we, as an organization, actually work with the code. So we're going to come back to the hotspots in a few minutes. But before we do that, I'd like to explore this topic in a little bit more depth. Because how can we get to 37,000 lines of code? How does that happen? Well, I think we have an explanation here. This is a book recommendation for you. This is a book called The Challenger Launch Decision by Diane Vaughan. And it's the single best book I ever read on how organizations fail. Now, Diane Vaughan, she's pretty fascinating because she's not a programmer. She's a sociologist. And she used the Challenger accident as a case study when she coined her theory called Normalization of Deviance. So how many of you remember the Challenger accident? Everyone that's like my age, that's good. So let me take a quick tour of the accident for the rest of you. So this is back in 1986. This is the final launch of the Space Shuttle Challenger. And what you see here, this is the actual space shuttle. This like orange-ish object here, that's the main tank with a lot of rocket fuel. And what you see here is something called a solid rocket booster. Now, the interesting thing here is that you might see this puff of gray smoke here. You see it? That's not a good thing. That's not supposed to be there. So what actually happened here is that those solid rocket boosters, they are huge, huge rockets. I think they're like 45 meters. So they are delivered in 3 separate segments that are then assembled. And it turned out that one of those joints in that booster simply failed to seal. So hot rocket gases were able to escape and impact and compromise the whole structure of the space shuttle. So it simply just disintegrated once it got into the air. And in her book, Diane Vaughan walks us through the history of the design of those solid rocket boosters. And she explains that already back in the early 1970s, where they did the first design tests of the solid rocket boosters, the first thing they noticed was that the actual performance of those boosters deviates from the predicted performance. That's not a good thing if you're going to send something into space, is it? So what do you do when you face a challenge like that? Well, if you're NASA, it's really easy. You form a committee. So they did, and they discussed the problem and decided to pass it off as an acceptable risk. Years later, during the first in-flight tests with the Space Shuttle Columbia, they again noticed that the actual performance of those solid rocket booster joints deviated from the predicted performance. Again, the problem was discussed and passed off as an acceptable risk. And it went on and on like that. They have several incidents over the next years. And it turned out that on the very eve of the final launch, there were some very serious concerns raised by some of the engineers working on the project due to the unusually cold temperatures in Florida at that time. And again, it was discussed and passed off as an acceptable risk. And the consequence was a tragic loss of human lives. So this is what Diane Vaughan calls the normalization of deviance. That each time you accept a deviation, those deviations become your new normal. You get a new point of reference. And the reason I tell you this is because the normalization of deviance has nothing at all to do with spaceflight and everything to do with people. People like us, people who build software. And we have plenty of normalization of deviance within the software industry as well. So just to give you an example, let's say that you inherit a file with 5,000 lines of code. At first, you might not be so happy about it, but work with it long enough, and you start to feel familiar. And besides, I mean, what difference does it make with a few extra 100 lines of code? So pretty soon, we have 600,000 lines of code, then we have 7,000 lines of code, and so on. So we need to find a way to detect when we become victims of the normalization of deviance. Here's one technique that I use for that purpose. This is something I call complexity trend. And the way they work is basically when I find a hotspot, what I do is I take each historic revision of that code, I pull it out of the Git repo, and I measure the number of lines of code, and I typically measure something like the cyclomatic complexity just for reference. And then I plot the trend over time like this. And the reason I do that is because every single system has a story to tell. We just need to learn to read them. So in this example, this was a piece of code I actually worked on myself. So what this story tells us is that here, somewhere in 2016, we did some kind of refactoring. So we actually managed to reduce the complexity. So you see, you can actually measure improvements too. That's good. But somehow we failed to address the real problem. So pretty soon the complexity starts creeping back in again. And here in early 2017, we have a very steep increase. And that's always a warning sign that we might have to take a step back and actually look at the code. The normalization of deviance is one of the reasons that whistleblowers are so important to an organization. And I have found that complexity trends make excellent whistleblowers in code. So to sum up this first part here, with hotspots, we're able to find the code with the highest interest rate. And the reason hotspots work is because all code isn't equal. What I want to do now is to show you how the same techniques scale to the architectural level and let us reason about system design and software architecture. So when we talk about software architecture, we typically want to step up and climb the abstraction ladder up from individual files and start to reason about subsystems and modules. And the way I do this is basically by introducing something I call logical components. So what I do here is basically I take a bunch of files, they might be in a particular folder, and then I simply aggregate them into a logical component. And basically, you can use any kind of mapping or aggregation that you want, as long as those logical components carry a meaning, a significant meaning in your architectural context. And then I simply aggregate all contributions to those files and treat them as a single unit when I do the analysis. And hotspots work really well, so we can basically get hotspots on architectural level. But there's usually an even more interesting analysis we can do. It's something I call change coupling. So let me walk you through that, because change coupling is a little bit different than the way we typically talk about coupling. So when we developers talk about coupling, what we typically mean is a dependency. I have a piece of code here, I use a piece of code here, they depend upon each other. But change coupling is different, because change coupling is invisible in the code itself. It's something we can only measure from the evolution of the code. So here's how it works. Let's say we have this simple system with just 3 different subsystems, 3 different components. The first time I make a modification to this system, I'm modifying the fuel injector and diagnostics module together. The next time I do a modification, I'm changing something else. And the third time, I'm back to changing the fuel injector and diagnostics module together. So now, if this is a trend that continues, we know that there has to be some kind of relationship between the fuel injector and diagnostics module, because they keep changing together like this. This technique is something we can use to evaluate the architectures and see how well they actually fit the evolution of the system. And I want to show you on two different kinds of architectures, and I'd like to start with one of the true classics. So, does anyone recognize this pattern? Yeah, it's a model view controller, right? One of the true classics of layered architectures. And it's kind of fascinating because when I come to a new client and ask them, what kind of architecture do you use? And they usually say something like, yeah, we have a model view controller or a model view presenter or something like that. And then you look at the code, and that's never what you see there. And the reason we don't see it is because we know when we talk about enterprise software, this is not enough. We need more layers. And we know that we need a services layer, right? Where we can put kind of like the business logic and that stuff. And below that, typically for in the .NET world or the Java world, what you typically find is that you need a repository layer. And the reason you need a repository layer has never been entirely clear to me. So I'm going to skip over that and just call it a best practice so we can get away with it. Sounds good? Right. And then below that, we might have data abstraction layers, or we might have object relational mappers, and then maybe at the end we have some SQL. And this is really just one example. In reality, you might have even more layers. You might have a business layer, view helpers, and whatnot. So architectures with 10, 11 layers is not uncommon. Now, what I do when I come across an architecture like this is that I treat each one of those layers as a logical component, and then I measure the change coupling on the architectural level. And what do you think I find when I do that? I find that the change patterns in an architecture like that typically look like this. In fact, I have found that somewhere between 30 to 70% of all commits that we do ripple across the whole architectural stack. And that lower number, that's for systems that are in a stable maintenance phase. So most of the changes you do are bug fixes, which tend to be local and maybe just touch one layer. And this higher number are for systems that are under active feature development. So that basically means like 2/3 of all changes you do, and you have to modify multiple layers like this. This is kind of interesting. Why does this happen? Well, the common motivation for doing layered architectures in the first place is what we call a separation of concerns. Do we have a separation of concerns here? Yes, we do. But we have a separation based on technical responsibilities. Each one of those pieces, each one of those building blocks represents a technical responsibility. So this is basically an architecture that's optimized for things like replacing the database with another database. We just need to change one layer. I've been a developer for 21 years. That has happened twice. So it is a real use case. But what we have to be aware of is that we make a trade-off here. We optimize for the rare case of replacing a horizontal layer, and we do that at the expense of the changes we do every single day, which is to add new stuff to it. And those changes tend to be use case oriented. They tend to be feature driven. So there is a conflict between what our architecture supports and the way we actually work with it. And this has consequences. In particular, I've found that layered architectures tend to work pretty well for small teams. We're talking about 2, 3, maybe 4 people. The problems I've seen with layered architecture, that starts when you scale the organization. When you add more developer to an architecture that looks like this. Because what will happen now is basically that everyone will work in the same parts of the code, but for different reasons, since they work on different features. And this is something that we're going to come back to in a few minutes. But before we do that, I'd like to show you a different architectural style. Because I think this, the expenses of working with layered architectures has been one of the drivers behind the recent hype of microservices. And as we all know, this is what microservices always look like in PowerPoint. In reality, we know that they are much, much more complex, right? We might have shared building blocks. We might have service templates. We might have client APIs. And we have cross-cutting concerns like diagnostics and monitoring. And all that additional complexity puts us at risk for one of the cardinal sins of microservice architectures. And that is strong coupling. Because the moment we start to couple the lifetime of different services to each other, we end up in a world of pain. And we lose most of the advantages of microservice architecture. And we are left with an excess mess of complexity. So if we have a fundamental architectural principle like loose coupling, why don't you use change coupling to supervise that? So what I do here is, again, I consider each service as a logical component, and then I measure the change coupling between them. And what I do is I watch out for stuff like this, when my changes tend to ripple across multiple services. And if I do this regularly, I can use this as an early warning system. And it's an early warning system that might help us avoid something I call the microservices shotgun surgery pattern. So the shotgun surgery pattern, that's basically when you want to tweak a single business capability and you end up modifying 5 different services. And there are several reasons why that happens. I think the most common reasons I have seen in practice is that, first of all, multiple services, they might share code that itself isn't stable from an evolutionary perspective. So the changes you do to a shared code ripples to other services. It might also be that some services API design is hard, right? So some services might just be leaky abstractions. So other services start to depend upon implementation details. And finally, I found that this pattern becomes more common when the same team is responsible for multiple related services. All right, I wanted to do something special for you today. So I thought, let's have a look at something I think you're all familiar with. Let's have a look at Python itself. So I sat down yesterday to do a hotspot analysis of Python, the C implementation. And it's pretty fascinating. I actually used to program a lot in Python. It's my second most favorite language. And but I never looked at the actual implementation of it. And I find it pretty fascinating because Python, it's a fairly large code base now, 1.1 million lines of code, so it's a big code base. Most of it is actually written in Python itself. It's the whole library part here is Python. But then the core of the language is implemented in C. So that's the parts over here, the objects, the modules. And I also find it fascinating that until yesterday, there have been close to 800 unique contributors. So Python is actually social design at a scale. Now, what I did was, first of all, I tried to identify the top hotspots here in Python. And I found one hotspot called typeobject.c. Is anyone familiar with that module? Cool. No one has looked at the code? We're going to do that. So what I found fascinating with this, Python is also great because it has such a rich history, right? So we see this file started its life in 2000. We see with the initial development here, a rapid increase. Seems to have somehow stabilized here, and then recently there's an upwards trend in the complexity. So if we have any technical debt in that module, it's technical debt that is likely to be worse now than it was just 3 or 4 months ago. So this is the kind of information we need to act upon. Now, what I did next was that I used the X-ray analysis because this is, again, a pretty big file. It's like 5,000 lines of code. So I did an X-ray on that one. And it's the number one hotspot on a function level inside that file is something called type new. And we see that, the final column here, cyclomatic complexity, basically refers to the number of branches, the number of decision points. So 166, that's like a factor of 10 more than the cutoff point for very high complexity. It basically means if you want to unit test this function, you need at least 166 unit tests. So this is most likely a pretty good refactoring candidate to simplify because we do work in that part of the code all the time. And we see that 486 lines of code, it's pretty much for a single function, but it's still on the level where we We could even have a single programmer. As a single programmer, we could actually refactor that. So we managed to take, again, that large code base and come up with a specific recommendation on where we should focus. But what I found so interesting is that, and the reason I show you this is because I want to show you that the hotspot concept, it scales on all abstraction levels. You can go all the way from architectural components to files and classes, down to functions and methods. And the same holds true for change coupling. So I showed you change coupling on architectural level. We can look at change coupling between files, or we can look at change coupling inside a file. So I want to show you one of the different hotspots in Python, the Unicode object. So this is a pretty massive file. I think it's around 15,000 lines of code. And what I did now was basically I parsed the code, and then I look at which functions tend to change together as part of the same commits. And I came up with the following list. So have a look at this. This was truly fascinating. So the way to read this data is basically, if we look here, we have two functions, Unicode find and Unicode rfind. Each time I change one of them, I have a predictable change to the other one in 100% of all commits. And that is not just a fluke. This has happened 35 times. And I think the reason we miss that as developers is because there might go a few months between the different modifications, right? So we as humans, we're not particularly good at keeping that in our head over time. But then if we want to look at the possible explanation, why should that happen? Why should two different functions be changed at the same time all the time? Some kind of strange quantum mechanics? Most of the time it isn't. So in this case, we'll look at the final column, because what I did here was basically a simple copy-paste detection. Just looked at the similarity between the implementations. And we see here that basically all of them that change together have a very high degree of code similarity. So what does that mean? Well, let's look at the actual code. And I hope you can see it here with the resolution. Here's an example of one of those pairs that change together. Can you spot the differences? So what we see here is a common reason for change coupling between different functions. What you see here is a dear old friend, copy-paste. So you see here, this algorithm is not really trivial, right? And we see that the only difference is that it's a different function that gets called here, right? So what we could do here is, even this is C, right? So our abstraction mechanism are a bit limited, but anyway, we could still extract the shared algorithm. We could parameterize it with a function pointer, and I could just send in the different variations here, and my duplication would go away. We have another example, a different pair inside the same function. This one is, I think it's even better. Do you see the differences here? So basically, the only differences here, there's not a single difference in behavior. The only thing that differs is the data. So here it says +2, there it says -2. Then we have the traces. So this is actually just the diagnostics traces, where one sense ends with, the other one sense starts with. So again, I would claim that it would be fairly easy to rip out a shared abstraction that actually represents the core of the algorithm and just parameterize it with a few concepts that vary. And if we do that refactoring, we can remove significant chunks of code, and our hotspot will become a little bit easier to maintain, with less risk that we forget to update one of those clones the next time we modify it. And all of that will be based on data from how we, as a community, have actually worked with the code. So to sum up this part, I want to show you that both hotspots and change coupling scale on all abstractions levels. You can use it on a system level, you can use it on a file level, and you can use it on a function level. Now, what I want to do next is to look at what I personally find the most interesting aspect of large-scale development, the social side of our code base. So let's have a look at the social side of our code. And before I do that, I would actually like to ask you, in your day job, how many of you develop software as part of a team? Almost every single one of you. Cool. Yeah, I do that too. We have to do that, right? And the reason we have to do it is because we take on larger and larger problems. Our systems become more and more complex, and there's just no way we can do it ourselves. So we need to get together in a team. And we all know about the benefits of teamwork, right? We always praise it as a genuinely good thing. And it might be. But what we rarely talk about are the costs of teamwork. So that's what I want to explore today. So I want to talk about something called process loss. And process loss is a concept from social psychology. Those of you who know me, you know I have my degree in psychology. It's like my big interest. And this is one of the things that I got truly interested in. So it's a concept from social psychology, but the social psychologists, they have stolen the concept from the field of mechanics. And the idea here is that just like, a mechanical machine, just like it can't operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. So here's how the model works. Let's say we have a bunch of individuals here. We put them together in a team. Together, they have a potential productivity. But that's never, ever what we get out of a team. The real productivity is always going to be smaller, and part of the potential is simply lost. How can that happen? Well, the actual type of process loss that you get depends on the task you do. But with complex and interdependent tasks like software development, I will claim that most of the process loss is due to things like coordination and communication overhead. And the bad news are that we can never eliminate process loss entirely. But what we can do is to try to minimize it. So let's look at one of the common reasons for process loss in software. And let's talk about the concept of diffusion of responsibility. So how many have heard about diffusion of responsibility? Some of you, 4 or 5, cool. So this is another principle from social psychology. And diffusion of responsibility, that's something you can experience if you're unfortunate enough to witness an accident or an emergency. Because what happens in that case is that it turns out the more bystanders, the more witnesses that are present, the less likely that any individual will offer help. It's a very scary thing, actually. And it's also a complex phenomenon, so there are multiple reasons. It's not like a simple explanation for it, but one of the common reasons is that the larger any group, the less responsible we as individuals feel. And we just assume that someone else might help instead. And this is really, really dangerous in real life, and it's actually quite dangerous in software development too. And I have to warn you now, because I'm going to talk about a very controversial topic. I'm going to talk about that stuff you're not supposed to talk about. I'm going to do something crazy. I'm going to talk about code ownership. Yes. And I just want to explain that when I talk about code ownership, what I actually mean is not ownership in the sense that, hey, this is my code, stay away. No. What I mean is that someone, and that someone, it could be an individual, it could be a pair in a large organization, that someone takes a personal responsibility for the quality and the future evolution of a piece of code. I simply don't think there's any other way around it, because the diffusion of responsibility principle, it's a very human thing. So, the diffusion of responsibility principle, I'm pretty sure that really, really good code is code where we have a sense of personal responsibility for everyone involved. And it's a frequent explanation for process loss in software. So if we have an important principle like that, how can we measure it? How can we detect if we become victims of the diffusion of responsibility, if we get coordination bottlenecks in our code? How can we do that? Well, remember, we are in version control wonderland. So we know exactly which developer that has written which part of the code. And what we can do now is that we can look, usually I don't find it so interesting to look at individuals. The interesting unit of measure is always a team. So I pull out the contributions from each individual and then I aggregate them into the teams. And then I plot a graph like this. It's the same kind of visualization, the same kind of enclosure diagrams that I used earlier for the hotspots, but only now the colors carry a different meaning. The colors show how fragmented each piece of code is from the perspective of teamwork. So basically, the more each team has worked with a particular piece of code, the more red that part becomes. And the actual algorithm behind that is something I took out of a research paper that I referenced down here. It's a really good paper, so check it out. And what this does is basically that it helps us identify that the more red something is, the higher the potential process loss in that part. Because if we have 5 different teams that all work with a part of the code, it's going to be expensive. The bad news are that it's usually pretty hard to act upon this data. So what I found in practice, what works best, is that when you find an area like this, where you have a high degree of coordination needs, the first thing I usually do is that I actually look at it from a technical perspective. Because code changes for a reason. And the reason a part of code attracts 5 different teams is usually because it has good reasons to do so. It has too many responsibilities. So by simply identifying those responsibilities and start to split that module into more cohesive pieces, we're not only improving the system design, we're also facilitating parallel work by different teams and different individuals. The second thing I found that is quite common is that some organizations, they just might lack a team to take on a shared responsibility. So sometimes you have to introduce a new team to take on a shared responsibility. Now, what I want to show you is that once we embrace version control data, we can measure a lot of things that we weren't really capable of measuring before. And I want to show you an example on how we can measure something called Conway's law. So, how many of you are familiar with Conway's law? So some of you, cool. So Conway's law is basically the idea that the way our organization looks will be mirrored in the way our software is structured, right? And it's usually a good thing, because when we align the way our organization looks with the way the code looks, we're actually aligning our communication paths as well. So what I do here is that, again, it's the same visualization style, but now the colors signals the operational boundaries of each team. That is, in which parts of the code do the different teams actually work. And you see, from the perspective of Conway's law, this looks absolutely wonderful, right? This is such a beauty. This is organizational nirvana. Because you see, each module here, each package is in the hands of a single team, and the team can work mostly independent of that one with a minimum of coordination needs. Unfortunately, I have a small confession to make here. All data that you have seen so far are from real-world code bases, except this one. I had to make it up because I'm yet to find an organization that's that well aligned with the code. So let me show you a more realistic example. The next one is from a real code base. Yeah, so this is an organization I worked with, I think a year ago. And what this organization actually did was that they had a component-based architecture. Someone went to a conference, and they learned about feature teams and thought like, wow, that's a great idea to shorten the lead times. So what they did was basically I took the organization and sliced it into 12 different feature teams. And then they launched them on the code base. They worked in iterations, 2 weeks iteration, and at the start of each sprint, each team was given a number of stories to complete. And what this data shows you is where the teams actually worked during a single month. Does anyone see any patterns in that one? Neither do I. And that's because what we have here, it's a small disaster. This is actually a complete coordination breakdown. Because what we see here is basically that all 12 teams need to work in the same parts of the code all the time, but for different reasons, because they work on different stories. So not only is this going to be incredibly expensive from a coordination points, this is the stuff that nightmares and merge conflicts are made of. But it's a bit more than that, but because it also puts you at risk for things like unexpected feature interactions, which are kind of like the worst possible bugs you can ever have. And besides that, I also think what you do here is that you miss synergies. Synergies between different features. That is opportunities to simplify not only the problem domain, but also the solution domain. So whatever you do, please align your architecture and your organization. Your code is going to thank you for it. And now, I have a few minutes left, so I want to show you the kind of tools I use to do this kind of analysis. First of all, it's pretty fascinating that you can get really, really far with just a Git client. So remember how I measured the diffusion responsibility, the fragmentation of each module? That's something you can do from a Git command line with something like this. So you basically point Git, It's a short log to a particular component, and you can basically see the fragmentation, which is pretty easy to map into teams. So if you just want to get some experience with these analysis techniques, I recommend just starting to playing out with the Git log. Once you want to analyze systems that are a little bit more complex, one possible option is an open source package called CodeMat. It's a tool that I wrote a couple of years ago, I think it's 6 or 7 years ago, as part of my previous book, Your Code is a Crime Scene. So CodeMat, it's still available. I still maintain it, and it's entirely free. What I've been working on over the past years is a tool called CodeScene. And CodeScene is the evolution of these ideas, so it's a way of automating all this stuff. And CodeScene is available as an on-prem, but also as a service, a free service for open source projects. So if you work in that space and you find this analysis useful, please consider to give CodeScene a try. Finally, this is a young field, so the tooling is still evolving, but there are some interesting options in the academic space. And one of my personal favorites is something called the Evolution Radar, which is particularly good at change coupling. So with that said, I really hope that you enjoyed our journey through this fascinating field of behavioral code analysis and evolving code. So ultimately, it's all about writing better software. Software that's able to evolve with the pressure of new features, novel usages, and changed circumstances. And I'm pretty sure that writing code of that quality will never, ever be easy. So I think that we need all the support we can get. And I hope this presentation has inspired you to investigate the field in more depth. And if you're interested in doing that, I put together a number of references for you. So I have 2 books on the topic. If you actually want to read one of them, I would recommend Software Design X-Rays. I think it's the better book, a brand new book. I also blog about this regularly at empir.com, where I have a bunch of different case studies. So please check it out if you're interested in seeing more. And then, of course, give your code a try at CodeScene.io. And now I'm going to hang out for a while. Unfortunately, I need to fly back home again, which is it's very unfortunate. But I'll be hanging around a while, and I'll be happy to take questions if there are any. And I also want to take this opportunity and say thanks a lot for staying here and listening to me, and may the code be with you. Thanks. Thank you very much.
Thanks. Maybe everybody or somebody have a question? Yes. I have a few.
Yes. So we have some code that is very slow moving, but should be fast moving, right? But is that something you've come across, and like how do you deal with that in those kind of analysis? Because it's just not going to show up probably. Because it's something it's too hard to change. It's dangerous to change. It's something bad.
Yeah, so I hear that every now and then. I've actually never seen it myself, but I heard yeah, I'd be happy to. So I heard about it. So it's basically the situation is, if I get you correctly, is that you have a piece of code that no one really understands. No one wants to touch it, so you build code around it, more or less, code your way around it. I do think there are 2 use cases. First of all, I think what you actually do is you already know that this is a problematic area. You don't need an analysis for that. And what I would do instead is I would take that code and treat it like any third-party dependency, because that's basically what it is. Like an opaque piece of code that you don't really look at. And I would focus on the code where you actually work and ensure that it doesn't end up in the same situation. Another use case I've seen is sometimes if you have access to the whole Git history, these techniques, in particular the hotspots and the change coupling data, is pretty good at. It's a pretty good support for onboarding. So what I could do in that case is also you could go back to the very history when that code was written in the first place and analyze it and see how the original developers worked with it, which might give you some insights to which part are the most interesting and what the implicit connections are. So that might be a possible use case. Anything else?
Yep. Hi, thanks for a really interesting talk. I have a question. So once you've done all these analyses and people have gone and fixed the problems, have you been able to measure improvements and how, yeah, basically that?
Yes, in some cases. I think one of the problems is that most organizations, they don't really have a way of measuring throughput or lead times. Those measures might be missing, so you don't even have a baseline. But some organizations do, and what I have seen, it always depends. If you do an analysis like this and you don't act upon it, it's only going to be depressing, right? But when we act upon it, we're actually able to pretty quick get some real gains. So the top hotspots, the numbers I have are typically that they make up like, as a rule of thumb, 3 to 4, maybe 5% of your total code base. So it's actually quite good news. If you have a real legacy code base, it's really good news to get that we don't need to fix all of that. We can focus on 3-4% and expect a real return on investment. So what I have seen are, I have one organization, they actually get a 10-time increase in throughput after spending I think they spent 4 or 5 months actually just repaying technical debt and improving it. But you always need to invest in it and act upon the information. And I also recommend when I'm refactoring code, I'm always being extremely careful. So I always try to make really, really small steps. I'm never after perfection, right? I'm just after a state that's a little bit better today than it was yesterday. And then I think we have to realize that it's going to be a process that's going to take quite some time. So I hope I answered your question. I at least answered some question, right? Thanks.
So I'm really interested in your coupling together with the histographs here, because one of the trends after a few years in the business is that most code gets written, touched a bit in the beginning, and then left to rot forever. And only once in a while do we have actually reason to go back and poke at it, and then everyone hates it, always. So how do you counteract that early abandonment thing from showing up in your graphs and showing up in this is a problematic hotspot, as in it's so intense development and then filtered off because, hey, it was stable and then not touched again?
So first of all, hotspots is a relative metric. So that means you're always going to have hotspots in your code base. And hotspots never mean that something is bad, right? So it just means it's a bit more important. So, and I'm yet to see a code base. Like I said, I have 2 or 250 code bases to analyze, and I always see that power law. Remember that one. So that means you will always have some code that do get modified, right? So that's your hotspot. So what you want to do now is you want to ensure that that code is really top-notch so you can continue to develop it, because that's where you actually work. So if you pick up that code and it looks absolutely beautiful, it's exactly what you want to see, then you're in a very, very good position. And it actually happens, right? So I've seen a number of code bases. If you want to have a look at an example, the one open source example I know about is JUnit, in case you're comfortable reading Java code. It's really fascinating. It's a 20-year-old code base, and it's still under active development. And you do a hotspot analysis, and you pick up any one of those hotspots, and it's very, very hard to come up with a suggestion on how to improve that code. It's really, really good. So these techniques, they might not be for everyone. I think that the biggest value you get from them is that it doesn't have so much to do with the size of the code base. It has more to do with the size of the organization. Because at some point, and I think that point is really low, like maybe there's just 10, 12 people, beyond that point, it gets incredibly hard for a single individual to keep a working mental model in your head of how the code actually works. And besides, a code base under active development, it's actually a moving target. It changes all the time. So I think once we reach that organizational scale, that's when I think we can actually benefit from this. So if you do a code base like you and 2 colleagues, I'm not sure how much you will gain from this. It would probably be fun and interesting, but I'm not sure about the value of it.
Yeah, hi. So I actually had been reading a little bit about the use of genetic algorithms and kind of ML approaches to doing code analysis. Actually, Facebook wrote a little bit about a tool they use to actually do to automate bug patch fixes, which was interesting. But I think the way that you're kind of explaining it is how I might think a little bit about it. So I'm curious, in that vein of research, while that may be focused to like bug fixes, do you have any thoughts or feelings kind of about that? And if so, what kind of things do you think might be interesting in this line of research as it relates to code analysis?
Yeah, so I don't have any insights into actual bug fixing, but bug detection is something I worked on. And I'm actually part of the research community myself. So, you know, that's another of my odd hobbies. I love reading research papers. So there are some, it's pretty fascinating because what I've shown you today, I don't like to call it a code analysis. I prefer to call it a behavioral code analysis because we're not really analyzing the code. We're analyzing the behavior of the developers writing it. So it turns out there is some pretty good research on that suggests that those kind of, what should we call them, like process metrics, like how often do you work with a piece of code, how much do you change, those are much, much better predictors of defects than any properties of the code itself. So I found it truly fascinating. So even if we can measure complexity metrics and nested complexity and whatever, and still much simpler behavioral metrics are better predictors. So I think that, I can't remember who actually did, I think it was Microsoft Research that did a paper on that a while ago.
I think it was very interesting to hear what you say, and I have a question about something you didn't say. And I think of this more pedestrian code review by your peers or by your boss. What role do you think that should have, or what is healthy level of code review?
Yeah, so I think there are two questions there. One thing I'm always quite careful with is that a code review should never really turn into a performance evaluation. And I think it's the same thing with these metrics. They are so particular social metrics. So if you look at CodeSyn, we have, for example, a way of simulating an offboarding. What happens if a developer leaves? And it could be pretty easy as a manager to sit that and say, all right, let's see who I can fire this week. And I think it's a misuse. And the reason I think it's a misuse is because even though version control data is pretty fascinating, it doesn't carry all your context. And besides, the moment you start to evaluate people, you kind of kill the team dynamics. Because what's going to happen if you put up a goal like, I'm going to measure on how many commits you do, right? What's going to happen is that the moment I find out about that, I'm going to do more commits. Each one of them is going to carry less meaning, but I'm doing more commits, and so on. Reward more lines of code. What happens is that all that code application we found in Python, I'm going to duplicate once more. So that's really, I always advise against that. So that's one of the things where I think this can be misused, and it ties in a little bit to code reviews. When it comes to code reviews, I do think this information might be useful. So one of the things I have been building is I've done some integrations with, for example, continuous integration systems. So one of the interesting things you can do is that, let's say you're analyzing a pull request as part of a review. One thing you can do is you can use the knowledge of change coupling. So for example, you can give a user a warning like, all right, you're modifying this part of the code. When your colleagues do that, they also tend to modify the part over here. Did you forget that? So you can catch possible omissions and things like that. And you can also, another thing I've been experimenting with is like your question earlier about predicting defects and that stuff. If you use those kind of metrics, you can usually predict the risk of a commit or a change set, which I think is really important in a code review because code reviews tend to become bottlenecks for an organization. So if we can get the risk classification in each one of the pull requests we have, we can actually use that to know that those pull requests, we can pretty much let them through because they are low risks. And these pull requests have a higher risk, and that's where we want to focus the reviews. So I think it helps in prioritizing. All right.
All right, thank you.
Oh. Thank you very much.